Okay, so okay. Here is the second week for Advanced Optimization Technique 1. We will discuss more on mathematical modeling. So after we discussed in the previous week about how do we represent optimization problem in terms of mathematical models, for for today's lecture, I would like to give you more detail on how we are going to solve those models. And one simple basic tools that you already learned in operation research, we will review it again today, in which we will going to use Excel solver to solve all those basic mathematical models. Well, I start from this basic example first because I think it's always good to have a good foundation for learning new techniques. And perhaps several of you, or if you are master degree student, perhaps you are coming from another background, it may give you a good stepping stone before we continue learning a more advanced techniques. Okay, and well, first, okay, the content I make the content a little bit concise. First, we will start about discussing what actually mathematical model is and where does it plays a part in optimization technique, or even a broader discussion in engineering optimization method, in which mean that how an engineer solve a problems. So for example, if there are a problem given to you, and as an engineer, what kind of perspective you can use to solve a problem, and then we can make it relate how mathematical model plays part on those approaches. And then we will discuss a little bit on, since in the beginning of the class, I already mentioned that, okay, we are going to learn the techniques, the tools, but we try to narrow the focus a little bit on how we do apply these tools in supply chain problem, in particular on supply chain network design, and how to use those tools on the problem related to uh, like selecting location for facility in supply chain, and such variants. So in the second and the third part, I will take one chapter from a book called Network Design and Application, in which they are discussing the introduction on how location related decision uh, um, are made from the perspective of optimization. And there we are going to discuss various dimensions being considerate in the location and decision problem. And after that, we will go back again with the problem that we discussed earlier in the first week, like transportation problem. And I will also introduce you a problem that quite famous related to that always discussed often in the optimization technique related topic, like shortest path problems, and we're trying to solve it using Excel solver. And I also have exercise if you want to like refresh a bit, because we are going to learn tools. It's always good to have an hands-on experience. So I will give you several well, still using the same example with the one that we used the previous week, but at the end of the session, I think I will give you some time to practice a little bit on those, like uh, hands-on experience on the tools. Okay, those are the contents for today. So let me start from the basic first. Okay, but before that, the course outcome we will cover, I think should be two course outcome for today's lesson. The first one is related to the first course outcome, in which you will be able to formulate mathematical models for after learning this session, and then you can have hands-on experience on solve those problems that you formulate in the mathematical models by using appropriate tools, in which in this session we will learn Excel solver tools. Okay, first of all, I will start with the uh, how can I say this one, engineering planning and design. So as an engineer, we have we can say common ground, or similar steps that is used by engineer on try to solving problem, engineer related problem, uh, uh, being faced to the particular to us as an engineer. And well, this engineers term here can be means people from industrial engineering, system engineering, or industrial system, or system engineering, or any general engineering in uh, any engineering in general. So basically, engineer focus on designing, planning, and managing complex system. And here in this slide, you can see engineering-based approach commonly consists of um, uh, this common step. First, when you have a problems, normally, when you face a problems that normally problems in the business process, or either planning, or anything that can be solved using engineer approach. Normally, first we will try to formulate the problem. It means that uh, engineers should try understood the problem clearly before try uh, to move forward to the next step. Well, we cannot talk about solution before we clearly understood the problem. So the first thing you need to do in any general engineering problems that you face is try to formulate the problem, try to define the problem. It doesn't have to, you doesn't have to do it mathematically, but in general, formulating the problem means try to understand the problem clearly, whether you try to find a definition, or what kind of function of those solution needed from your for the problem that you are going to use, or you need to define the environment or of these problems being faced, or who are the users. Those are the first step that you need to conduct as an engineer for during the planning of design, or of a solution in your proposed solutions. And then after you have the a good definition about your problem, you can move forward to collect data related to the problems, and analyze those data to see whether your assumption when you formulate the problems is matched with the data and the condition that you met in the field. Okay, so uh, that's why the arrow that you see here is is not just one step process. There is a returning process when you collect the data and you find, when you analyze those data, and then you try to relate it with the problem that you already defined earlier, and you find some mismatch, so you can always go back and iterate the process. So it means that all these steps has the possibility to return to the earlier phases, since that um, every step we might find new information, we might find new correlation with the previous step that you might want to fix it before you move forward. Okay, and then after you find a good formulation of the problems, find relevant data to make some analysis, and you already have the basic understanding on how the solution, what kind of solution might work for those problems, you can generate several alternative solutions. Okay, several alternative solution, you perhaps for, if one condition is met, you try to provide one alternative solution. If another condition will met, so you try to provide another alternative. Then based on this, it doesn't always have to be two alternative or three, but it should be adequate to respond to the problem that you face in this design. Okay, and after you have generate the alternate solution, you can evaluate those design alternative. Okay, and to evaluate this design alternative, there is several way, right? You can play with the real system, like you have those alternative, you can try to have a pilot project implemented on the real systems, but sometimes it's not viable cost wisely. So sometimes you need to use modeling techniques, either the techniques that you learn in advanced optimization technique part 2, like using simulation techniques, or you can also use the one that you will learn here in advanced optimization technique 1, using mathematical modelings, or even you can also make like some engineering make like a mock-up of the system. Okay, like a physical system but in a similar in a smaller scale. For example, let's say aeroplane model, that those are a mock-up of the real system but in a smaller scale. Or for example, for an architect, they make a building, a construction site. They also, we, even though right now nowadays already we see 3D implementation of architectural design, but sometimes we also see the mock-up of the buildings in the in the smaller or scaling size of the real design. And then after you evaluate the design, there is several way to evaluate, right? For example, if you are using simulation, there is a parameter that you want to see what kind of, let's say, if you are simulating the queuing system, how long the queue will be using the first alternative or the second alternative. Or if you are using mathematical model, you will want to see the objective function. What will happen if you use the first design? What will be the objective function? And if you use the second design, what will be the objective function? And then after that, you can select and specify the design that you are going to use in the real system. And then after that, we are after several iteration process, we will make sure that okay, we can really implement those design in the problems that happens in practice in the field. Okay, those are engineering planning and design process that is common in general. Well, whenever, even even during your research, you can also reflect the way of doing research is kind of similar to do with the way we conduct design, or we find design a solution for from engineering perspective. Okay, like when you formulate your research, it's similar with how to formulate problem. When you try to propose a method for your research question that you formulate, it's similar with how you generate alternative solutions. Okay, so basically these are, there are similarity in doing research and uh, 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 design, create a solution, design a solution in the perspective of an engineer. Okay, if you are interested with the book, I can always provide you the link to this book. But if you search, I think you can always find it, this one, uh, supply chain engineering book. Okay, then where mathematical modeling played part on that engineering process. First is mathematical modeling is one of the basic tools that you can use in engineering design process that we discussed earlier. Well, as the name as the name represents, mathematical models is that you are using a model to represent a somewhat an abstraction of the real world system. Okay, in this case, because it's a supply chain book, so when you create a mathematical model for a supply chain problems, so it's a supply chain model in which it is normally a simplified representations. So you won't be able to, okay, this is one of the drawbacks. You won't be able to represent all the complex possibility happen in the real world systems, but somehow this simplified representation or this abstraction should be able to be used as a consideration for your decision making process. Okay, so uh, several study also mentioned that when you use model, it means you should already uh, um, realize that model will not exactly represent the real system. Okay, model can be seen as an idealized or a system in ideal environment. Okay, so we can call it idealized representations, and it is often structured or defined purposely. So the modelers or someone that create the models is often structure or define the model in purpose to exhibit some specific characteristic of the problems. Okay, so the example is here is more general, like, okay, when you want to make an aircraft model for your tunneling wind tunnel experiment, for example, so your model is purposely made in ideal conditions so that those aircraft model can give you some insight how the aircraft or yeah, how the aircraft will react on those specific experiment. I'm not really familiar with those those aircraft experiment, but what can I say is mathematical modeling has the similar or um, the same approach, in which whenever you want to see or you want to experiment on real case problems, a mathematical model will try to replicate in a simplified manner, on in an abstract point of view of of those system, but somehow we will try, or a modeler will try to purposely, or doing it in purpose to exhibit some characteristics that you want to analyze. For example, later we will discuss about transportation models. So a transportation model that we will discuss later won't be able to represent the real situation of transportation system in the supply chain networks, but it's somehow designed to purposely give you tools to analyze how demand and supply and network usage costs is affected each other. Okay, for example, if you have one high demand in one node and one high supply in the one other nodes, and you understood the cost structure of each network link, what your solution would be. Nah, those mathematical model can help you to make those kind of decisions. Okay, well, I think, yeah, this one, the one that I just mentioned. Okay, before we go further on the location decision model, I think I will give 5 minute breaks as our as we agree on. After 15 minutes discussion, we have 5 minutes breaks. To, if you have a question, please, you can raise the question. Okay. Okay, before that, I want to see. Okay, now after we talk about the basic understanding about engineering process design and mathematical modeling in general perspective, now if you well, of course, like we mentioned in the first week, there is a lot of application of optimization techniques, mathematical modelings in many fields: marketing, operations, supply chain. And last week we already discussed that in order to have more uh, narrow discussions, I'm going to introduce you how we will apply those optimization techniques in terms of supply chain planning, supply chain optimization problems. In particular, we want to see today is how optimization technique can be applied to optimize location related decisions. Okay, the optimization location decision is has been discussed in many books, many literatures, and in particular, I find these books from Daskins 2013 entitled Network Design, Network and Discrete Location Models is quite complete in discussing this matter. So mathematical models is often used to provide at least an insight for a decision maker in terms of their location related decision. Okay, for example, several questions that raised during those type of decision are like, how many facilities should be used. For example, if you running an e-commerce, for examples, let's say, well, Indonesia is one of a good example of how facility, the 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 decision related to facility will determine how competitive you are. For example, in terms of e-commerce, well, in Indonesia now have like at least two big player or three big player in terms of e-commerce company. We have Shopee, we have uh, Jingdong from China, J and D, JD. They have the localized brands. They call it J and D dot ID. The one big player, and we have Tokopedia, nation one of the national products for e-commerce. Tokopedia, Shopee, Bukalapak, all those are e-commerce company, startup company in Indonesia uh, that right now operating in Indonesia. But as you understand that one of the key factor determining how e-commerce can compete is how good they can serve their customer. Okay, but Indonesia has in particular geographically challenged network, transportation networks. For example, well, if you are in one of the most populated islands in Java Islands right now, like me right now in Jakarta, the capital, it is so convenient to get those products from e-commerce. You order it today, you can decide when you want to receive the product, the same day or the next day, or just the regular, like it depends on the service of the logistical party. But for the one that in remote area, for example, another islands that little bit far from the distribution center of this e-commerce, that will be a challenge, because let's say you order today, you cannot make sure the delivery in the previous years. Like you maybe need at least 2 to 3 days to receive your products. Okay, so one of this deciding factor for the competitiveness of this e-commerce is how they can expand their distribution center facility. For example, recently what I saw is like Shopee or JD now opening more facility to serve the east part of Indonesia. So it means that they are trying to reach more customer by investing on those facility. Okay, but the question is, how many facility you need to serve all those demands, and where those facilities should be located, how large, how many capacity are necessary, and um, and so on, the similar question that I pose here. So basically the question related to location decision is similar to what are shown in the slide here. And then yeah, here are several examples of location related problems. The one that I just mentioned, how to decide where you need to put your warehouse or distribution center. And or another similar but will have slightly different objective and characteristic on the problem, like how do you open a new branch, where you should open the new branch. It will depends on the demand of your product and so on. Or another challenging or like more contemporary issue, for example, like during this COVID situation, perhaps we can use the mathematical models to analyze how the vaccination and health facility in our location to analyze how the facility related to vaccination and health facility to help to alleviate the demand of a COVID patient. Is it an adequate or not, or should we invest, or should we need more facility, or if it is needed, where we should locate those facilities, something like that. Mathematical model can take part on this kind of uh, um, uh, this type of problems. Or another things in which this one in particular I am currently researching this with my master degree students here in Indonesia, is that the demand of electric vehicle is rising. It's already, we can already see it in China, in India, or even it's already getting stable demand in US and Europe's. But somehow in Southeast Asia, like the Philippines, Thailand, uh, Indonesia, we can see the rise of the demand, but the facility to support those electric vehicle, I think, is not adequate yet. So if we want the demand is how to say, if we want to get the sooner or later we will at the phase that we need to provide those facility to be able to implement this technology of electric vehicle. One of the most important facility is the availability of charging stations. Yeah, we know that mostly electric vehicle will be charged at home, but somehow the availability of charging station, public charging stations, is necessary to let the public more convenient and more trust on the adaptation of the electric vehicle. So we can also address this problem as a mathematical model problems on like the same, how many of these facilities needed, where you should put the facility, and on what capacity and stuff. Okay, those are the introduction on what we will learn in the, I think, the next week, on how to model the optimization location decision. Okay, and in particular, when you address the location problems, okay, we classified those type of decision as a location problems. You need to also know about various dimension of location problems, so that you can address the problems in a proper mathematical approach. It means what? When you know these characteristics of the problems, then you can select the right or the the correct mathematical implementation. Here I will try to introduce several of it. There is many that may not mention here. But let's start from the basic. First, there is location problems based on the data, whether it's planar data or discrete data. A planar data is representing a location model in which the demand can be represented in commonly denoted as coordinate in the maps. Okay, it can be any particular maps, like Cartesian maps, like we normally use in calculus, represent in the x-axis and y coordinates, and or in the real maps. For example, you use the longitude and latitude of the some particular locations. Okay, so that type of location problems is classified as planar problems. Meanwhile, the other way is you know the locations, but for the every other attribute you will provide it with the data. For example, you don't know exactly where does it located in the maps, but whenever you want to understood what is the distance, for example, from one location to another location, you will be provided with the data. Those are discrete location. Okay, and since we discussed about the distance earlier, so distance is one particular one important characteristic of location problem. When you talk about distance, you need to understood that choosing the correct way to measure distance will determine how you analyze your problem. For example, when you want to measure distance in locations that located in city blocks, for example, in the city, it's normally if the city is well organized, it normally consists of several blocks. So it normally measured using Manhattan distance. But if you can measure the distance using a straight line, for example, you want to use what uh, let's say you want to deliver product using drone, so it's using air network. So you can assume that, okay, because there is no obstacle in the air, even though in real it's maybe not like that, but you can simplify the assumption. Okay, we can measure the distance from one point to another point if we use the air network using Euclidean distance. Or if you are using the longitude of one city to another city, then you want to calculate the distance. There is a particular way called Haversine distance, in which this measurement take account of the Earth curvature. So we assume that Earth is round, and the curvature of one location to another, the curve one location with another location should be taken account when you measure distance. So you use Haversine distance. Or you can also always use the online maps services like Bing Maps from Microsoft or Google Maps by Google to provide you with this data. Okay. There is several others like static and probabilistics. I already mentioned in the first week. What kind of problem can be represented as a static problem? What kind of problem can be represented as dynamic? And what kind of problem can be represented as deterministic? And what kind of problem can be determined as probabilistics? So in this one, I will skip those explanation. I go directly to the um, various dimension of location problem related to there is we can represent location problems in terms of their objective, whether it's a single objective or multiple objective. A single objective problem, it means that we want to focus on one particular decision factor. For example, if you want to minimize the cost, okay, minimize the cost of allocating facility. So this one is the only objective you want to achieve in your model. So this can be considered as single objective. But if you have, let's say, more than one uh, uh, um, objective that being trade off with each other. For example, okay, I want to maximize the demand being served. So you need to allocate many facility, right? The more facility, the more demand you can get. That's the one logical how to say one logical explanation. But it depends actually. But let's say it's like that. One is maximize demand, another is minimize the number of facility. So there is a the one um more than one objective that is being trade off with each other. So this type of problem is considered as or classified as multiple objective problems. Okay, another thing is in more specific to the facility the location problem, in which you consider a capacitated facility location or uncapacitated. A capacitated mean you consider how many the capacity being can be served by the facility that you consider. For example, it may be the amount of area in those facility. If it is a warehouse, for example, those are capacitated facility. Okay, this one, the second 15 minutes before we go to the more specific discussion on modeling, mathematical modeling, we will have 5-minute breaks. And I think I saw several new participant. Let me see. Okay, now the first mathematical model that we are going to review is called transportation problems. Okay, so what is transportation problems? As I mentioned earlier, whenever you do a mathematical models, it would be the simplification of real problems in the practice. Okay, for example, the one that we mentioned here, transportation problems, the mathematical models that represent transportation problem that we discussed today is represents uh, as you can see in the figure on the right. Okay, so for this particular transportation problem, we will consider a set of supplier source with each supplier has unit of supply represent by capital S with index I, where index I is an index that represent each supplier. Okay, and this particular supplier represent by set of supplier I capital will supply customer from that represent by on the right side as destination nodes or demand nodes, in which each customer will have their amount of demand necessary to be fulfilled. Okay, um, in this particular transportation problems, we will try to find which supplier uh, will uh, will provide product to which customer, and those product will be supplied from which link. Okay, so we have 1 2 3 it will be determined by the cost of shipping from one particular supplier to one particular customer. Okay, so the unit of cost supplying from one supplier to another customer is different one to another. Okay, it represented by unit cost of shipping product from one supplier to another demand point. So it represent by the CIJ. Okay, C from I, supplier I to demand point J. Okay, so we will find the shipment pattern from which supplier will supply which demand points. such that the cost of those supply and demand pattern is minimized. Okay, okay. Let me show you the example for this one. Okay, for example, okay, before we go to the mathematical models, um, let's say you have here, wait. My pen drive, my Wacom is not connected yet. Let me set it up first. Okay. Okay, now it's connected. Uh, let's say you have 40 from here, you have supplied 30 from here, and you have 30 from here. And here have 30, 40, and 30. Okay, each of these connection will have a cost. For example, here you have 5 costs, here you have 10, 5, 11, 12, 13, 14, 15, 10. So you will try to find the demand, the supply and demand pattern. For this one, which supplier will be supply those demand? And using, it means that based on which nodes here, right? So for example, if you want to supply the node 1 using from 2, so you need to consider there is 11 unit of delivering cost from 2 to 1. Okay, but if you are using from here, from 1, supplier 1, the cost is only 5. Perhaps the model will select this one. Okay, so those are the type of problem considered in the transportation problems. Okay, in mathematical models, there is at least 4 things need to be considered. First, when you want to formulate the problem, you need to understand what kind of inputs are being considered or what kind of parameters. Earlier, we can see that we know how many demand and how many supply are associated in with each supplier nodes or I element I. This is the set of supplier. Okay, and then we also have the same representation for demand for each particular demand nodes or index J. This one is the set of demand nodes. Demand nodes. Okay. And the last one is we will consider the cost related to shipping unit from uh, a particular node I, supplier node I, to particular node demand node J. Okay, this is represented by Cij. And to select to represent the solution, we will use decision variables Xij that represent how many the amount of product is shipped from supplier I to demand node J. so that the total cost can be represented by the total of cost multiplied by whether we are using how many units we are shipping from particular nodes I, which the supplier, to the customer nodes J, Xij. And when we total this, we will have the minimum shipping cost, total shipping cost, right? Because this is the amount of products and this is the cost of the shipping for each product. Okay, and of course to make these models works, we need to uh, uh, we need to state the constraint that each of the demand out from the total demand out from a particular supplier, this one, for all I, it means like for each supplier, I represent supplier, right? For each supplier, we will check the total demand going out from that supplier, that particular supplier, should be less than the total amount of product is able to be supplied for the supplier from that particular supplier. It means like this, wherever you have this one, a supplier, SI, right? For example, if you have here 50, so here, this is Xij, right? When the total amount of this Xij, let's say if you already have 40 here, the total amount from this one and this one should be at most 50, because you only have 50 to supply it from this particular supplier, right? Either this one 55 or this one 0 and this one 10. This represented by the constraint number 2. Okay, and the same way we need to model the constraint for customer or the demand point, in which that the total amounts of product supplied to the each customer or demand point should be less than equal to those demand point itself. It means what? If I draw it like this one is the demand point. Okay, for example, if they have this demand point D1, for example, need only 40, so you should be provide this one at least 40. Okay, 10, 30. You cannot provide them only 10, 10, and then 10, so it less than 40. Okay, you should be at least 40. So 10, 30, and then here is 0, for example, like that. These are represented by the constraint number 3. Okay, and the last is that since this is the amount of products, that the variable Xij represent the amount of products, so the amount of products flow in one link should not be less than 0. So Xij should be greater than equal to 0 for all I to j. Okay, these are the basic mathematical model for transportation problems. Okay, now we talk about solution approach. Well, I have several video here. We can categorize the approach for transportation in two type of approach. First is the heuristics approach, in which this will show you how we can get a feasible solution. It means that the solution that can be really implemented, that is not violate any constraint. Okay, but it may be not optimal, may not optimal. Okay, Why does we need this type of solution? This can be used as an initial solution, or if you have problems that is going to be solved several times. For example, you want to use the method in the simulation, you can use, because in simulation you consider the uncertainty in a different way. It is being simulated, but for each different condition, you want to have a good solution that can be done fast, right? Okay, so you can use the heuristic approach. So the solution will be feasible, but it may not optimal. It is often represent the real situation, because in practice, people normally not use exact solution or mathematical approach, but they are rather using the easier way to implement, or but at least it give you a feasible solution, but it has a good quality. Okay. But the one that we are going to learn here is mathematical programming or exact solutions. Why? Because mathematical programming can give you, can guarantee that whenever they found a solution, it will be an optimal solution. Optimal solution means that this solution will be the best solutions considering the constraint that you state in the mathematical models. Okay. And there are several ways to use this. Like you can, for exact solution, you can use simplex method, Excel solver, or mathematical programming. Okay. Okay. Before I give 5-minute breaks, I plan to show you these videos, but since this is copyright from YouTube, so I will stop the recording first. Okay. Discuss. Okay. Now we try to discuss more on the exact solution and mathematical programming approach. Since the heuristics here, if you want to, let's say you want to study again about the Vogel's approximation method, northwest corner or minimum cost, you can always see those videos that I provide the links here. And for mathematical programmings, there is actually, or exact method, there is actually a particular method that can provide you the optimal solution, so-called transportation method, for simplex method for transportation problems. And there is a tutorial also here in YouTube, you can use it. And today we will try to use I will try to give you a demo on how we use Excel solver to formulate these mathematical programming formulations and try to get the optimal solution using these tools. And for mathematical programming in particular, we will use MPOL, one of the mathematical programming approach that is often discussed in many books. So I try to find, and I think I am able to get the software. The license is for education purpose, so that we can use this for our class, and it has the fully function full feature like what we use in the business license, but it can be used in the teaching and learning situation like what we have right now. But this one we will discuss later, perhaps in the 4th weeks. So you in the research, you are most often use this one instead of the Excel solver. Okay. But for today, let's try the transportation problems using Excel solver. First of all, of course, we want to find one particularly good examples that we can play with today. And this is called balanced transportation problems. Why? Because the amount of supply here, the total amount of supply, will be equal to the total amount of demand here. So it's called a balanced transportation problems. if the total amount of supply is not equal to the total amount of demand, there is some particular things you need to do. For example, you need to introduce dummy nodes and so on. But for that one, I will suggest you to explore further. For today, I will just try to introduce you the basic of how we can solve these transportation problems and find the optimal solution for these balanced transportation problems. Okay, demo using Excel solver. Okay, for those that already in the groups, I already provide you with the files that I'm going to use today. So you can also open the file while I explain it in and demo it on the screen. Okay. Um, okay. Let me open the file first. Transportation problems. Okay. Here. Cool. Yep. Okay. I hope you can see the screen here. First, here I try to provide you the modelings formulation again from the same slides that we have. And on the right side here, I also provide you with the data that we are going to plot in the Excel solver here. And the feature that we are using here in particular, you can find it in data and solver here. However, if your Excel is not yet shown this one, I guess you can always activate it in from here, from wait, add-ins and solver here, solver add-ins. And then you can try to activate this one. For me, fortunately, I already activated. If not, you can try to activate those one. Okay. And the first thing you need to do for I normally try to follow this type of format. I want to as much as possible to be similar with the notation and then the step that I use in modeling the problems in their formulation as well as it's translated to the Excel. So first, for the input, I will provide one input in particular. I will have this one. The SI will be supply here. This should be SI. Supply available is this one is SI. Okay, and here will be the demand, the DJ. Okay, so here will be the, if you see here, we have supply A, B, and C. A, B, and C, we have the amount of supply is 140, 130, and 110. 140, 130, 110. Okay, it's associated with the cost, associated with the supply here. And for the demand point or destination here, you have here 1, 2, 3, 4, here 1, 2, 3, 4, and you have 70, 50, 125, 135, 70, 50, 125, 135. Okay, oh, you have the data out here. Next, you need to put the cost here. For example, from A to 1, A to 2, A to 3, A to 4. The cost is 5964. So 5964. A to 1 is 5, A to 2 is 9, A to 3 is 6, A to 4 is 4. Okay, the same way you need to put it for B and C. Okay, next, for the decision variables, first of all, this actually should looks like this at the beginning. Okay, this also like this one. Okay, this one also like this. at the beginning should be look like this. Okay. For the supply here, the decision variable is you want to select how many amounts you will ship from I to J. So you will create a 2 by 2 matrix. Here you will have the index I, here you have the index J. This will be your decision variables. This is the Xij, XA1, this one XA2, and so on until here XC4, this one. Okay. And then for the objective, you want to, this one, will be the total. Yeah, you want to minimize the total a1 xa1 multiplied by cos a1 plus, yeah, all the sum product of this one multiplied by this one. So you can write it here as Excel has the function of sum products between this multiplied by, sorry, sum product of this and this. Okay. For now, it's 0 because all here is 0. For example, if you have a particular 10 ship here, so it will be called 50 because 1 multiplied by, 5 multiplied by 10 is 50. All the rest is 0, so it's 50 plus 0, something like that. This will be changed by the solver later. Okay. For this, that one is for the objective. For the constraint, you need to state it one by one here. You have for all I, it means for all the supply here, you need to check the total amount shipped out from the supply should be less than equal to 140. So what is the total amount supplied from the nodes A? Going out, sent from supply A should be equal sum of all of this one here. And also here is sum of this, all of this here. Okay. This one will be sum of all of this here. Okay. And for this one, for the second constraint, constraint number 3, we will have the total demand arrive at the nodes I1, 2, 3, 4. It means that you check for all nodes J element J. It means that for all demand nodes, you will make sure that it is supplied in the amount of that is at least as it's requested. So the amount of product arrived in one will be equal to this one. This one will be equal to this one, sum of this. And this one will be equal to sum of this one. This, the last one is, okay. Okay. That are the setup that is the setup that you need to be able to use later for the solver. Okay. After you have this setup ready, you can go to the solver menu here. Okay. This one I already create this constraint one by one. But for the sake of example, I will try to reset it first. Okay, first we need to set what is the objective value. The objective value will be calculated based on this one. Minimize the total cost, right? That we already define the formula here. And we want to minimize it. And the decision variable will be based on this one. Change this column, change this cell in the Excel. And then for the constraint, you need to set one by one. Here should be less than equal to here, and then this one should be less than equal to this one, and left hand side is this, right hand side is this one, and this one, but the no, sign is different, greater than this, this greater than this one, and this one greater than this one, and the last one is this greater than this one. Okay, then yep, 1 2 3 1 2 3 4. Okay, we have all of that, and make sure you check this one. Make unconstrained variable non-negative is for the this one, xij greater than equal 0. Okay, and there are several methods. We can use the simplex method. It means that they will use simplex algorithms that you can see how it's implemented in the video, but it's conducted behind the scenes, so we will not see step by step of the simplex here. Okay, then you can solve the problems, and here you can keep the solution in the solver, and you can also create, sometimes you can have the sensitivity analysis report and limits report, and this one is the topic for another session. But for now we will try to see the result. Okay, we have the minimum total cost is 1,800 based on this decision. Okay, so if you see here, the total amount of that out from the A is 140, out from B 130, out from C is 110, and the arrived product at 1 2 3 4 all is equal to the demands needed. So this solution is feasible, and this is the solution that you need to use for to get this minimum objective. Okay, and I think that one is for the demo for transportation problem. I think it's still quite simple, but I hope that this gives you one refreshment about this topic. The next topic, before we go here, I think let's have 5-minute breaks while discussing about what do you think about that approach for Excel solver. Okay, maybe let me ask first for PhD student, have you familiar with this approach or not?
For me, Dr. Satri, Dr. Wira, yes.
I think it's quite simple, right? This is like the basic that you learn if you do, if you taking industrial engineer, industrial management. At least if you already study OR, this should be like very 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 easy task. But for what about master degree students that taking this class, maybe Ivy or Joshua, have you ever using these tools before or not? Hello. Maybe if you don't have the microphone, you can chat so that I understood the how far I need to go again in detail. Okay, maybe not yet. What about other PhD student other than Arvin? I'm sure that this should be also easy, right? Should be
Yes,
okay.
sir. It's familiar for me, sir.
Okay. For the rest of the class for this one, we will uh, still using the same example because I want my students to be really familiar with this one and will be able to uh, use this Excel software anytime you need. It means like this is one weapon at your disposal whenever it needs, because I'm sure that you may or may not find um, mathematical programming approach or algorithms to be code whenever on whatever situations, but on any situations. But I think Excel will be always in your computer. So I think whenever you have one simple problems, you can always use this one. So let's move to the next topic. Um, regarding to this one. Wait, what is it? Okay, the next model that we would like to discuss is so-called the shortest path problems. Okay, this one also a model that is being discussed in many literature, many books, and it is considerably one important problems um, in terms of optimization problems, because uh, we can see that well, one of the most popular implementation is that the things that we always use nowadays. Whenever you use GPS to find the uh, uh, the shortest path to find a route from one location to another locations, behind the scene of those programs is always an optimization problem, so-called shortest path problems. The implementation may be different, the algorithms that they use may be a little bit different, but the basic is the same. Okay, it's all shortest path problems. So for the shortest path problems, the characteristic is like this: you will be given a network, of course, networks, transportation networks that consists of nodes and links. Okay, we represent nodes as a set of nodes N and link set of nodes A. And each links is associated with a cost. Cost, the same way we represent it as Cij, is a cost associated of using link I to J. If you use this link, there is a cost, for example, based on the distance, perhaps. Okay, and since it's a shortest path problem, so you will have source or the origin nodes, where do you start, to the, and also you will have the destination nodes or your finish, the finish of your journey. Okay. um, okay, based on this one, we can also, this is not often, but we can normally people not discuss about the mathematical formulation of shortest path problems. Why is it? Because it is not the same with the one that we see earlier for transportation problems. For transportation problem, heuristic like northwest corner, minimum cost, Vogel approximation will not be able to provide you with an optimal solution. That's why you sometimes need mathematical formulations to use your mathematical solver to get optimal solution. But for a shortest path problems, many heuristic algorithms is proven to be able to give you an optimal solution. Okay, so sometimes, most often, we will not find a mathematical formulation in a shortest path problem paper or shortest path problem study. They will directly discuss the algorithms. Okay. But for the sake of learning how the mathematical solver tools can be implemented in the shortest path problems, we will try to find models that can represent shortest path problems. Okay. Okay. If we want to model, we can see there is similar way. We always have these four components. First, we will have the inputs. Input will consist of the origin nodes and then the destination nodes. The cost traversing, it means that when you use those arc, there is a cost associated with it. And this will be the data or the input that you use to for the supply to the models. Okay, this can be the distance, this can be the traveling costs from one place to another place. And for the sake of this formulation, you need an additional parameter that define a set of nodes. So you have set of nodes n, right? Then you will make a subset nodes that associated with each node to represent which node uh, uh, directly connected before and after these particular nodes. Okay, if I want to represent, if I can draw a picture to represent this set, these two sets, AI and BI, we need to draw it for each particular I. I represent the particular nodes here, right? I. So set of nodes AI here, AI here. So it means it's related to the nodes I. It's sorry, BI here. It's the node that is connected before I. Okay, this will call BI. And then the nodes that going out from I or connected after I will be represented in AI. Okay. This also often called the correlation metric. So whenever the nodes correlate with each other in a particular nodes, we can call it this one. Okay. And this one will be used to represent the connection of node in the models. Okay. It's a little bit hard to look here because you don't see the implementation yet. Okay. First, okay, we have this one. Keep it first if you don't understand it, but later after you see the model, I hope it will be easier to understand. Okay, then for the decision variables, here we write it differently. Previously we write x, I, j, right? Because normally x, I, and j is considered as a separate entities. But here we consider it x, I, j in one entities. Okay, it's a combination. It's a combined together. Okay, so a pair that represent a link from I to j. Okay, if this link is being used, so the value of the decision variable is 1, but if not, it will be 0. For example, if you have here, okay, for example, like this. This is 1, 2, 3, 4. Let's say we want to find the start node here and the finish node here. We want to find the shortest path from 1 to 4. There is two options, right? 1 to 2 to 4, 1 to 3 to 4. Okay. This, if you want to represent the solution um, of 1, 2, and 4, this will be equal 1, this will be equal 1. Okay, so that's how we represent the decision variable for shortest path problem. And meanwhile, if this one already 1, this should be 0. Xij here should be 0. Here Xij should be 0. Okay, then based on that information, we can formulate the objective function is the total cost um, of the path that you are using to get from your start to finish node. Okay, and the tricks to make the start and finish node here able to make a route that we want, we need to create this one. Okay, this will be utilized to formulate if the start node, if the node is the start node, the total value of the going in and going out should be equal to -1. Okay, this one, total value of nodes going in and going nodes is -1. And if the nodes is the destination, should be the total value of incoming and outgoing should be 1. Meanwhile, if the node is in the middle, okay, sorry here, the total sum of direct nodes going in and going out should be 0. It means what? For example, like this. Okay. If this is your start and then the destination here, the total nodes here should be -1. The total going in here should be 1. But if you are in the middle, should be 0. Why? To give you here is 1 and here is 1, the xij. So that it will be delete each other, then it will be balanced from the going in and going out. Because if you put here is 1, the decision or the solution will not make a particular path that you want as a shortest path problems. Okay, so this is the big trick that they use to represent shortest path problems. Okay, and this one can be calculate before we put it in the mathematical models. Okay. Okay, well, next we will try to solve this one. Let's say we want to go from here, from the source to the destination here. We will try to formulate it in a mathematical way in using Excel solver. Okay, for the solution approach, of course, this one will be mostly discussed in the literature using heuristic algorithm, because the heuristic algorithm for shortest path problems for some condition can assure optimality. That's why it's more interesting, because it's fast and can assure optimality. So why should you use a mathematical problem for this one? That's why many, when you discuss shortest path problems, mostly people will suggest you to use heuristic algorithm instead of mathematical formulation. Okay, but still we can use mathematical formulation to solve those problems. And that one, the one that I will show you for today's lecturer. Okay, for the one that in the groups, or I think I already also send you the files for this one. So let me open that file first. Shortest path. Okay. Okay, here you go. First, actually there is several way to model this one. This is one particular way that I use, that I think it is more easier to understand to represent this one. But somehow if you want to make the model as it represent in the mathematical formulation, it is also possible. I maybe want to I maybe I will introduce you to the way to represent the model as it's formulated maybe in the 4th week, when we discuss about using mathematical programming like MPulse to solve this one. Okay, but first, for this one, as I mentioned earlier, I normally use the same step. I will provide the input first and then state the decision variables, and then formulate the objective, and then fill the constraint one by one. Okay, first for the input here, we will need source and destination here, source and destination. We want the source from node A to node H, and from A to H here, we will have the cost traversing matrix. Okay, and for each non-connected node, non-directly connected nodes, I put a big number 9999, so that it will not be selected here in the decision variables. Okay, so here the initially it should be 0 like this. And the objective, it's still the same. It is the sum product of the cost matrix multiplied by decision variables. And for the constraint, okay, this is the way, this is the a little bit different way we understood the constraint here. For this one, it is really look like this, xij, xij. However, for the sum here, you need to calculate all the incoming nodes to A and total outgoing nodes from A, okay? And sorry, let's go F13. Wait. Let me check first. Okay. Okay, I think the formula is wrong. For incoming nodes, okay. For the start nodes, the right hand side should be -1, total right hand side here. And for the destination node should be 1 here, okay. And here you need to calculate all the incoming nodes to node A. So it should be actually here. And from here should be all the outgoing node to, so this should be outgoing node from node A. So this will be incoming node from node A, okay. And this should be, okay. I think, yeah, it's updated because it's already solved the problem earlier. Okay. And the left hand side to represent this one, sum of incoming is minus sum of outgoing, okay. Okay, then now you can solve the model using here, data, and then solver. And the objective is here to sum product of decision variable multiplied by the cost matrix. And then for the decision variable is this one, okay. And for this, you need to state that the decision variables here should be a binary variables, because it's not the same with the previous one that it is only constrained to be a positive number, okay. And for this one, the left hand side should be equal to the right hand side here. Okay, I guess it's like that. Okay. Then make sure unconstrained are non-negative variables, simplex, and then you can solve it. Okay. Wait, why is it coming here? Yeah. Okay. Here you can see the solution that the minimized total cost is 34, in which the solution is from A, you start and wait. From A, you go to F, and then F go to D. From D, go to E, and then from E, go to H. Okay, those are the paths. A, go to F, F, go to D, D, go to E, E, go to F. Okay, So that's the solution. A, D, E, H. Okay. Sorry, A, F, D, E, H. And the total is A7, A to F7, 7 to plus 5 is 12, 12 plus plus 14 is 26, 26 plus 8 is 34. Okay, this would be the minimize the shortest path from A to H. Okay. Later on, what if I want to go from A to G? Yeah, you need to change this one to 1 and this one to 0, something like that. Then you solve it again. Okay, these are the shortest path problems. And okay, yeah, I think those are the introduction for using Excel solver to solve the mathematical models. And for today, we already learned how to formulate mathematical models and then several heuristic algorithms to solve those particular models. And if, until we try the how to formulate those models in the Excel solver and solve it. Okay, for now, we still have 10 minutes. For master degree students, I will ask you to submit this one as an exercise. I will grade those exercise based on how correct you formulate these two problems. Well, these two problem is actually a simple multi-period inventory models, and I think it is easy to solve for using Excel solver. So that's why I provide you two example exercise, and I already fill several format to use, so that you just need to fill the value based on your understanding of these models. And after you finish with those exercise, you can submit it to my emails or to the Blackboard. But maybe I suggest just do both in case I cannot, you cannot access the drop Blackboard, or just for the sake of we have the backup. So you can submit to my emails, and you can also submit to the Blackboards. I think we can try this one, so that you will not have too many homework for this week. You can use this 10 minutes time, try to finish this one. And if you have any question, I will stand by for this 10 minutes to help you and guide you to for this exercise. Okay, I think for the class for today, for the material is up until this one. Okay. Other than that, if you have any other questions, please you can ask now also.